Well, welcome everyone to this one of our first fireside chats with today Essam Metwally from Merck. And the general subject is going to be when does the prediction earn you trust? And we're going to have a very open discussion about this with Essam, but also we really encourage conversation from you guys as well who are attending. You can see a QR code there for attending Tipium, so you can update on what we're up to. But if we can go to the next slide, that'd be great. Kind of what I said. Please, yeah, feel free to ask any questions using the Zoom Q&A button. We'll be answering as we can. We're quite limited in our responses here, but we'll do our best afterwards to answer those questions. And we'll record the entire webinar, and that'll be available on the website. So you can come back to it later, and others, if they're not attending, they can see that. So next slide, please. That's about me. So I'm Nathan Brown. I'm Director of Science here at Tipium. I'm leading the Research and Application Science team. I previously was Director of Digital Chemistry Helix, building methods and platforms there, and also at Benevolent AI, building the Chemical-Informatics and Computational Chemistry team. I've done a bunch of other stuff, as you can see, written a few books, published some papers, developed some stuff. So, but this is not so much about me, it's more about Essam. So I think we can go to the next slide, and I can give a quick overview, Essam, but I'd like you to introduce yourself in a moment. So Essam's been at Merck since 2018, over 20 years working in drug discovery and algorithms, and both in the lab and in silico. And I think this is a really essential point that we will get to in the conversation, that integration between the lab and computation. PhD, all the right stuff, all the smart stuff. And he did a lot of postdoctoral work in Scripps and work on X-ray crystallography and cryo-EM. So it's my pleasure to welcome Essam today. And yeah, Essam, if you want to introduce yourself more clearly than I have, obviously.
I appreciate it, Nathan. We've known each other actually quite some time ago.
Yeah.
I was just starting, and you were also just, I think, a budding postdoc. At any rate, it's actually been, I think, now for 26 years, but it has been a trip. As Nathan indicated, I kind of started at the lab. Bench chemistry, biochemistry, and then ultimately going into medical science to develop salivary gland peptides and anti-anaphylaxis and septicemia drugs and peptides. That eventually evolved towards the end of my thesis into computational approaches when really the field itself was quite nascent. And I ultimately found myself at Scripps working on, from a in silico standpoint, reconciling X-ray crystallography with this new field of cryo-EM and trying to fit structures into these amorphous blobs to try to better understand what these proteins looked like and how they behaved. And that really informed on a lot of what came next, and I think where our field is today. From Scripps, I moved on to Tripos, working on early versions of Sybil and for those who are not familiar with Sybil, because it's actually quite old at this point, that was probably the premier software for molecular modeling. I think actually they were the inventors of molecular modeling software at the time. That ultimately I moved on to CCG, or Chemical Computing Group, where we worked on Mo. And finally, I decided it was time to go back to the other side of the bench and actually apply the algorithms and software that I had learned or coded and bring those to bear in the pharma industry at Merck. And that has been the last several years, 8 years now, 9 years. Yeah, I hope that was concise enough.
No, that's perfect. Thanks, Essam. No, I think for this audience as well, it's interesting for them to understand how you went from, I can't really say from the bench to the lab, to the bench to the computation, to the, but what drove you towards where you are now?
Hubris. No, it's the in part there is that aspect to it. I had started from a young age coding and programming, and so I hit university and said, why am I going to waste my time doing something I'm already getting paid to do as a programmer? So let's apply it to something else I find interesting, which is biochemistry. And so I spent the next several years working in that vein. So, but everything comes full circle ultimately. And so, even as I was going through my thesis, I frequently found myself coming back and trying to say, how can we do this better? There are ways to predict. There are ways
Mm.
to examine structures in silico that we just can't access from the bench. And this idea that you could actually examine and look at structures and look at small molecules and understand how they were working at an atomic level without ever leaving your computer was always fascinating to me. And I recall actually one of my candidacy questions was essentially an open-ended question, but it called for a research proposal. And I remember my colleague reading it and said, "This is what you were meant to do. Above all of these other questions, this is the most clear, concise. This is
Yeah,
an amazing response, and it's clear that you understand what goes into it from the outset."
yeah,
I think, like I said, sometimes you struggle to go away from what you know, and you're
yeah,
inevitably brought back.
yeah. It's interesting to me because I kind of come from the other side where I was doing computation and I wanted to do something more useful than making a blog blockbuster video database or whatever. I wanted to do something useful with software. So I feel we're at that conjunction where we're truly translational from algorithms to applied science, and we're meeting in the middle in that way. So that's a useful place to start, I think, because it means you've obviously you've seen from both sides. I have done some lab work.
Mhm.
It was not my finest moment doing chemistry and doing other things, but you've seen it much more than I have from both sides from the bench and the model. So let's talk about how we really stand. So if we talk about AI in drug discovery, where do we sit at the moment? For a start, what do you think people misunderstand about AI and what it really means in drug discovery today?
Yeah, so let's start with an easy one, I guess. No, it's this. I think there's a lot of hype, but we're still in that hype cycle of what AI is and what it can do. It's extremely useful, but in the sense that it allows us to explore the knowledge we already have more so than where people think it is, which is this generative component. And I think and when I say generative, I mean actually coming up with new ideas, coming up with new suggestions that are actionable and can and we can move forward on. I think that is actually the misunderstanding of where we are today, and it doesn't take a lot to see, what AI is actually doing. AI itself or ML, all of these algorithms are really just advanced statistical machines, which are good at predicting what it has seen come after what you are asking. And so when I say hello, uh, it knows that in 90% of the time, the correct response is hello or how are you? And so those are the things that are being exploited, and it applies just as equally to chemistry or whatever the representational token happens to be. And so I think where we are today is we are good at uncovering the underlying relationships within the extant data. What we are not good at doing is extrapolating beyond that domain. And so you see this over and over, which is it will predict, it will do a good job of prediction if it's been trained properly on properties that are within series or within common molecules. But the moment that something fundamental changes within that scaffold or within that structure, it loses context, it loses position until you are able to train it again with that new information or new data. So I think we are a long way from a truly generative state. Um,
Yeah,
we may have
that,
drifted a little bit there, but yes.
but no, it's great. We've got quite a few questions, but yeah, one of my bugbears is this just about representation in our chemistry space and biological space, or is it something? Are we missing something more fundamental we're not measuring?
I mean, the question about representation, we've taken to talking about tokens and about
Yeah,
tokenization and how things are broken apart. I don't think that whether we're talking language, whether we're talking chemistry, biology, really anything, the token itself doesn't matter. We like to think that it matters, but the token is just, for lack of a better word, the atomistic representation of these models. And so it's capable of putting together tokens and ideas that it has been presented with or trained with before. I don't think it is a matter of representation. I do think that some of the, if we're talking specifically about chemistry, I think some of the representational approaches are better. So, for example, why do you see better results with biology? It's because, in some respect, the the atomistic portion is actually concealed within a more generic concept of an amino acid, and that amino acid behaves more predictably, more has this more fundamental set of properties which are ascribed to that allow you to do better or allow you to complete better predictions on the results. Whereas when you look it down to an atomic level and you say, I have a carbon, and I have another carbon, and I have another carbon, and all three of those carbons are completely distinct from each other and have different properties, and actually, owing to position, owing to connectivity, owing to aromaticity, they behave completely differently and have completely different results. And so there is an aspect which is related to representation of atomistic structures, but at the same time, I think that while that might be solvable, I don't know that it gets at the fundamental problem of novelty or extrapolation.
Yeah. No, but I agree with you to a great extent. So that's the state of play where we are now. We have genuine progress in what we're doing, but there is a real gap between that claim and that progress. So we've seen that algorithmic progress. We're doing well on benchmarks. We're demonstrating utility from those benchmarks themselves, but are we showing utility in application of AI itself? So this is a hot topic at the moment. It's like, where are we really making the differences and applying AI to drug discovery, from your point of view?
I think it is actually living up to some of the expectations, which is, certainly for us and for others, this notion that we can predict more and
Yeah.
experiment less. I think that is actually happening. I wish it was more predictable about some of how these properties behave, but I do
Yeah.
think that it is actually in specific instances and specific properties, it's doing an extremely good job being able to predict novel chemicals or novel series within those with those properties, which doesn't completely get rid of the need to experiment, but it does greatly reduce the number of compounds or structures that need to be tested in
Mm.
order to validate or verify. And so when you start to see those patterns emerge, you get become quite, I guess, excited because it means that if I'm spending less time and money on this
Yeah.
experiment, I can spend more time and effort on where it really matters in improving potency or improving necessarily the properties that are not easily predictable. And if I do a good job on predicting solubility, then I may, even though I have designed or figured out, okay, this compound is going to be extremely potent, but if it's not going to be
Mm.
dissolved, then I'm not going to bother making it. And
Yeah.
let's look at ways to improve that solubility before we even get to the point of
Yeah.
synthesis. So I think we are actually succeeding in that domain. Not
Yeah.
linearly, not across every single property, but
Yeah.
definitely across enough of those properties that it is actually having a significant impact on cost and realization.
Yeah. No, I mean, I've definitely been able to use, say, solubility models. I built, as we all have, many solubility models based on data, which is not that
Mhm.
useful, but we can get a straight line, and that's not,
Yeah.
a straight line is not that informative. So I just wonder what makes a difference to allow you to make a decision rather than just good statistics. What
Mhm.
gives you confidence to use a model in anger in a project?
You said two things I think which are important there. Let's seize on the first one
Yeah.
because, I think it's a fundamental flaw is not the right word, but it represents a schism in how the two groups see it. Well, as experimentalists, we talk about, or experimentalists or machine learning or algorithm developers, we talk about
Mm.
these correlation in R square. We want to see that perfect line of prediction. But as an experimentalist, that's actually less important than having a yes no decision. And can you categorize this as a true positive? It's basically your matrix: true positive, false negative, and true negative. So the better you are able to make those predictions and you have those cutoffs, this is where I've seen it excel, because we tend to actually shoot ourselves in the foot. We say, oh, the correlation is only 0.6 or 0.5, and when in actual fact, it's actually doing a very good job at categorization. And
Yeah.
we say the model is trash. So we move on and we keep on doing these experiments. But for the experimentalists, they've actually seen exactly what they need to see. And I've seen this time and time again. We have two or three categories. And as long as we're able to make good predictions within those categorizations, then the experimentalist is not as concerned with the actual direct prediction of the exact or precise value.
Mhm.
So I think that's a important piece of knowledge for the algorithm developer. Maybe even though we really want to be able to predict, the fact is what is actually actionable, and that's more
Yeah.
important. That's the first aspect, I think.
Mhm.
The second point that I wanted to raise, based on your comment, was data.
Yeah.
The data itself is so fundamental to this entire world that we live in at this point,
Yeah.
where you really need high quality data. High quality, not just high quality data, high quality curated data, which has been handled consistently, which we understand how it was produced, where it was produced, and how consistent it was when it was being produced. That's actually quite a rare thing, and, it's unfortunate. I think being at Merck,
Mm.
I'm in a privileged position. We have over 100 years worth of data, and it's all very well maintained.
Yeah.
I'm not saying that all of it is necessarily usable, but the vast majority and the consistency with which it is maintained and versioned, and that's something which is rare across, I think, not just the industry, but across fields, across. It's just nobody really anticipated at some point
Yeah.
that we needed that level of diligence in maintaining the data. And so
Yeah.
I think a lot of attention has to be paid to those foundational aspects of what data is, where it's coming from, and how you can actually draw predictions or draw conclusions from it.
Yeah. No, no, I completely agree with you. And I remember spending a lot of time cycling across the Rhine in Basel, from Gross
Mhm,
Basel to Klein Basel, to get data off people's hard disks. And those data of their spreadsheets are not the data I needed to make a
mhm,
good model. So there's also an aspect here about what data should we be generating
mm.
that helps us build better models. Do you have any thoughts around that aspect?
It's going to fluctuate so much depending on the
Yeah.
questions you
Yeah.
ask.
Absolutely.
So it's not something I think we can necessarily get at. And sometimes I think I to go back to this idea of, let's take AlphaFold as an example.
Yeah.
Um, many years ago when I started and I learned about homology modeling and this concept of taking an unknown sequence, looking for a actual sequence where we had structural representation, then using that as a template. One of the first things that had occurred to me was, well, what if we didn't use one template? Let's use all the templates. Now, at the time, there wasn't a practical approach
Yeah.
to doing that, and in some cases, the data could be potentially overwhelming. So it's something that I sidelined. I was very happy to see when AlphaFold and these other programs came
Hmm.
along that had applied almost exactly that idea of multi-templated approaches to creating these advanced models. But the structure is only one aspect there, and
Yeah.
to go back to this idea of what do we need to measure. It's known unknowns, right, or unknown knowns. We tend to look at crystallographic data, for example, or cryo-EM, or these structures that we see represented as being the absolute truth. And in
Yeah.
fact, they are also just models and representations of single
Yeah.
points in time and condition. And so we need to understand the data itself and what we are asking, even before we can truly draw informed. decisions from it. So
Yeah.
if I have a structure,
You've gone on mute, I think I said. No, you're back, I think. Oh, you're off mute again. Take
there you
it.
go. AlphaFold, for example, is good at predicting these crystallographic structures or these representations that it has seen before. And I've seen this time
Yeah.
and time and again. You guys brought up my paper on the PKG
Mm.
alpha prediction.
Yeah.
And in that case, I saw numerous examples where it was so heavily biased by existing structures that it couldn't break away from
Yeah.
that, even when new data was introduced. In particular, because we just had this conversation, but in particular because some of that new data was not in direct lineage. So part of those new structures were PKG, protein kinase G beta, and so
Yeah.
the model itself didn't have a concept that beta and alpha are the same, or that they may have related properties or related structural features, and so it never was able to draw conclusions based off of the new structure that could be applied to the old structure. So it's things like that, and I think if there's this goes to this point about having a human in the loop, having a
Yeah.
hypervisor, having somebody being
Yeah.
able to describe or inform what is actually important. Where should my attention
Yeah.
be?
Yeah.
And so,
So I guess in that example with the candid structure, you're almost, you could argue, you're overtraining to biology. You're
Mhm.
over understanding a very narrow field of the protein structure, its cooperation that wasn't allowing you to understand more widely. But this brings us on really naturally, I think, to talk about human in the loop and what is our purpose as scientists, human scientists. Now we have
Mhm.
various LLMs helping us with stuff, and I use them every day. I will not ignore that fact. But what is our utility, our purpose in this loop, in your opinion?
Um, so I don't think it in some sense it hasn't changed. We are to be that critical oversight.
Yeah.
We are the engine for ideation. We are the ones designing or asking the questions. The
Yeah.
LLM doesn't ask us questions. It doesn't understand that. It doesn't understand the concept of question. It
Yeah.
understands I'm trying to exploit these statistical relationships.
Yeah.
But swap one value for another value, or swap again, it comes back to this idea of tokenization. The token
Mm.
itself, or what the token represents, is not relevant. It doesn't know. It doesn't actually have an
Yeah.
understanding. And so, we are enamored, I think, by the illusion of intelligence that we are seeing.
Yeah.
And I had the conversation with my daughter, and I say it again. It's because they're like, it's intelligent. It's able to have a conversation with me. I said, well, how much of that conversation is actually truly unique or novel? It just
Yeah.
knows that this is how it should be answering. And it's kind of scary that it can be so indistinguishable from intelligence as to be
Mm.
mistaken for intelligence. But I really do want to underscore that it's not intelligent. And so we can't get away from the human in the loop, because the
Yeah.
human in the loop is what is actually driving the course of that conversation and the course of those questions, and is actually deriving meaning, because without that human, there is no meaning to the responses.
Yeah. Yeah. No, no. Yeah. I really agree with you on a lot of
Mhm.
this. So based on this discussion, it's where should we be investing now in software, but also where we're doing stuff in the lab? What is the most important thing for us to be doing to help develop cures for diseases that help society and humans?
It's in that acquisition of the data.
Yeah.
The AI itself, or these models, they can't do any better than what the data is providing.
Yeah.
And so, that's probably one of the most critical components, is being able to generate sufficient amounts of data that we can actually make or exploit those meaningful relationship underneath that can then be
Yeah.
used or leveraged to make predictions. Um, it's still going to come back to this concept of, we say that what can we do to produce better molecules or exploit or treat disease. It's still going to come back to, how can I make those more actionable? How can I make the models better? And if we can't have the data. And it's not just the data that we are thinking about. I think we need to take a critical look at the types of data that we are trying to produce,
Yeah.
because
Yeah.
the data itself, again, is coming back to things that we have traditionally used as our metrics. But if we were to take a step back from that and say, I believe that this aspect, let's say aromaticity, or if we're talking about, say, solubility, or if, just to make it a simple example, but if we were to talk about this resonance or these other metrics that we maybe hadn't considered in the past in terms of how they applied to a specific feature, it's how do you aggregate all of that data into something which becomes a more meaningful model?
Yeah.
And I think the other aspect there is, how do you step away from this tendency that we all have to
Mm.
mistake models for ground truth?
Yeah.
Uh, a crystal structure is a model.
Yep.
It's a model which a lot of effort and time and money has gone into, but it's still ultimately just a single model. And yet we predict, or we are predicating our decisions and our structures or the things that we design based on those models. Again, using that assumption that they are the ground truth. And then we're
Yeah.
surprised when there's failure, or when something doesn't quite work out. And that's not because that there was an issue. It's because that the model itself needs to be refined to accommodate for those
Yeah.
conditions. Where I was headed with that is, again, there's this idea of confirmation bias, and I think we are this anything that has happened with AI is, we have ended up in a positive feedback loop of
Yeah.
confirmation bias. We
Yeah.
are asking a question, we kind of know the answer because it exists in the data already, and we're looking for that answer, and we are happy when we see the answer.
Yeah.
And then we
Yeah.
assume that there was failure because the answer hasn't been displayed. So it's
Yeah.
this endless loop of confirmation bias. And again, it's about this tendency. I've always said that you always want to be able to publish negative results. Negative
Yeah.
results are just as valuable, or if not more so, than positive results. And yet we still lag in being able to publish those or
Yeah.
discuss them and use those to adequately train our models.
To what extent, and just leading on from that, I guess, to what extent do you think orchestration of oracles in that loop? So it's human in the loop, but there's also oracles. So the
Mhm.
NSA that's automated in the lab, but obviously much more efficiently docking or pharmacology search or whatever else you want to do.
Mhm.
What aspect do you think that has as part of this ensemble?
I think it can be quite valuable, again, as
Yeah.
long as you're able to collect that negative data
Yeah.
and make use of it. And so, when I talked about us being myself being in a privileged position to have hundreds
Yeah.
of years of data, I think more important than actually, it's equally important, is as that positive data is that negative data, because I can mine numerous structures, high throughput screens, results where millions of structures which would have otherwise not been
Mm.
tested in a given assay, they all have data for that they
Yeah.
potentially all have data for that assay. And so I can see what worked and what didn't work
Yeah.
in a glance, and train off of that. So I
Yeah.
think that's where we can have a massive advantage. And until we can kind of break that paradigm, this generative
Mm.
dream is going to be that for quite a while. It's just going to be a dream until we can actually leverage the knowns and the unknowns.
Yeah. Yeah.
Mhm.
Yeah. That's terrific. So,
Mhm.
it resonates a lot with me, as you know. But I guess, yeah, we're come to the end of our time, or we're actually a bit over. But I'm just thinking back. I think we're in quite a luxury situation ourselves, where we grew up in a place where we didn't have anything like this. This was sci-fi, totally. This is not even like modern sci-fi. This was completely blows our minds. What would you encourage people to look at in the next 5, 10 years or so to make a difference for drug discovery, which is where we've ended up?
I would say that, if you are interested in AI, and AR AML, and you
Mm.
are interested in drug discovery, uh, the two are moving hand in hand.
Yeah.
I think I'm not discounting this fear of AI
Yeah.
that is real to some extent. In the same way that when we were coming up, we always talked about the low hanging fruit of drug discovery.
Yeah.
There are obvious ideas. There's the intuitive things. There's the simple leaps, which didn't require massive amounts of compute to figure out. I think we've largely moved past that, but that doesn't mean that what we're seeing now isn't the same thing. Everything
Yeah.
is cyclic, and so AI is also exploiting, in its own sense, this low hanging fruit. It's able to see these relationships because it's looking at everything at a scale that we can't
Yeah.
necessarily conceive of or have the time to look at, but it's
Yeah.
exploiting those underlying relationships. But, you know, I would say that, it's a great time to be doing that, but again, you have to always, as a scientist, take a critical view and critical eye
Yeah.
to what we're actually asking. Look for those non-intuitive things where you can say, "You know what? This other series is quite related, or this other set of compounds, or
Yeah.
this other protein is related. How can we leverage that information to inform my models?" Because it's only going to train on what you're actually going to allow it to train on. And
Yeah.
so if you consistently only give it one point of view, then don't be surprised when it only returns that same point of view over and over and
Yeah.
over again. So
Yeah.
I think it's about this critical eye towards training. And, you know, I don't think chemists in general are going to be displaced anytime soon, but don't be the person who's only looking for that simple solution. We need to be thinking,
Yeah.
and how do we synthesize these more complex questions? Because those are the ones that require, I think, a lot of oversight from us as the
Yeah.
scientists in order to
Yeah.
direct our AI to the right area for exploration.
Yeah. And it's also, you talk about synthesis. It's not synthesizing the most complex molecules. What is the molecule that's going to help you answer the hypothesis you have at hand?
Yeah.
It doesn't have to be the most expensive, most complicated. It doesn't have to be analog by catalog either. It can be very simple.
Yeah, I'm glad you brought that up. I actually I
Yeah.
wanted to say it earlier, which is, you know, one of the things that we see is you can see where a model is starting to fall short, and I think AI actually
Yeah.
helps us there.
Yeah.
You know what? If we just had information in this particular area, can you synthesize this molecule? Let's answer that question. Then it
Yeah.
becomes a relationship between you and the AI to
Yeah.
say, this complements, all right, you're missing data here. Let's synthesize this molecule. It may not be our blockbuster. It may not be our
Yeah.
the primary compound, but it's going to help us inform on all of the future compounds and give us better results.
Yeah. No, absolutely. I remember one time when I joined the ICR in London, I took all the structures we had. I did an argue deconvolution of 300 structures and then built up a virtual library. And I rediscovered a, uh, a functional group that I thought that something odd happening here. And I went back to the chemist and said, why aren't we pursuing this? And he said, oh, we did do that because it's mouse liver microsomes, but now we're at HLMs, human liver microsomes. Now it's not a problem. And they're like, yeah, we should make more compounds like that. Just that
Mhm.
simple switch. It's not really computation. It's just rediscovering what you already knew that helps you make a difference, in that decision making, which is, I find endlessly fascinating. It's that humans, we're full of these biases that we forget about. I should probably go to the questions. I'm sorry to, yes, I'm sure to follow up on that. Or,
No, I was just going to say, you know, again, I think you just said is actually important, but in maybe a different way. It's that conversation. Again,
yeah,
we keep focusing on this AI and how can AI improve and what are we doing? But, you know, the more important question was you heading to that chemist and asking that
yeah,
question, having that conversation with the guy who's doing the synthesis.
yeah,
And it's that relationship that I think is underutilized.
yeah,
As a modeler, I think one of the first things I was told when I went into industry is, "Oh, chemists are going to ignore you. They don't wanna hear your ideas." They think that hasn't been my experience, but I think part of that is this collaborative aspect.
yeah,
It's having that conversation. I mean, I know it's a shock to a lot of people, especially the younger ones, that you should be talking to your colleagues, but having conversations is critical because
yeah,
it gets everybody on the same page and there is a buy-in that
yeah,
happens when this collaboration occurs.
yeah. Now, I won't hog the conversation, but I've got
Mhm.
do have two anecdotes around that where,
Yeah.
again, when I joined the ICR, the guy held the database in a leverage folder in his arms. That was the data. So I couldn't access it. And the second one was when I joined there in London, chemists wouldn't talk to me. So what I did is I put a jar of sweets on my desk, and the chemist would walk by and like, oh, he's got sweets. So it's a little bit of social engineering as they come in, they'll
Yeah.
eat a sweet, and then like, oh, what do you do? Why you got so many screens?
Yeah.
What's all this about? So there's a lot of, that human interaction. I think is hugely powerful. Let's go to some of the questions. So Marcus Metz, hi Marcus, good to have you again. His medchem colleagues always want an explanation, not just a prediction. What's your experience in that aspect?
I don't think that they're necessarily wrong.
Yeah.
The question really is, you're suggesting something. Why should I listen to you? And
Yeah.
I think that's the more fundamental part or aspect to it. You can say that I built up a relationship or that when I make a prediction and I give it to you, that's just a number. And I want to know the why. And I think that's important.
Mm.
You should be any chemist or any machine
Yeah.
learning person, you need to know the why. So, again, I think we benefited from having grown up and come up when we weren't just predicting one-off numbers from statistical models.
Yeah.
We actually had to understand what was the underlying relationships that were going on, how the
Yeah.
model fit. So I don't think it's an unreasonable question. And until you can prove or you can demonstrate across large swaths of data that your model is actually predictive and doing what you think it's
Mm.
doing and is able to recapitulate actual results, then until that time, then the question about why is actually an important one.
Yeah.
When it becomes established science, then you can say, here's my prediction and this, and the
Yeah.
why is the model said so.
Yeah.
But until you can do something like that, then you actually have to dig into the actual data and understand what those relationships are and why it may be predicting in the way it's predicting.
It's a counter argument to that
Mhm.
based on cognitive bias, that it looks like what I'd expect, so therefore it must be right. Is
Mhm.
there something around that we also have to challenge as
Yeah,
good scientists?
I mean, you have examples of magic metals, right?
Yeah.
Uh,
Yeah.
I think
Precisely.
magic metal is the most intuitive argument
Yeah.
there is that just because it looks like something doesn't
Yeah.
necessarily mean that it's actually going to do what you think it's going to do. So, I have an example uh, where the change in position of a single oxygen
Yeah.
has profound implications for transporter properties, PGP.
Mm. Yeah.
And
Interesting.
just by shifting that oxygen one atom on the ring, all of a sudden this PGP liability disappeared.
Yeah.
There is not a single model that predicted it or could predict it.
Yeah.
It just happens because it just happens in this case because of fundamental atomistic properties that are not and that similarity or that cognitive bias
Mm.
that this looks like this, therefore it should act like this. That's not something that is actually holds true in the bulk of the chemistry that we're actually doing.
Yeah. And I think this, I'm just reading the questions as well at the same
Mhm.
time, but I think this plays well to the way you were talking around not just data generation, but the design ethic of the generated data. So what data should we need to build better models that helps inform better decisions and better discussions? I'm just conscious of time.
Mhm.
We're a bit overrun. Is there anything you'd like to finish with a final thought, SM?
No, do we, what time is it? Do we still have,
We have a little bit more time.
time?
Well, we have as much time as we like. We're over what we scheduled. But if people are willing to listen, then we'll be
Yeah.
uh,
No, I wish we were at a stage where the models were good enough that we don't need to understand. We can
yeah,
just take it as fact. If anything, the last 6 or 7 years have shown me is that is not the case, and
Yeah.
that we are surprised more often than we're not.
Yeah.
It's yeah. To Marcus's point, that's we
Yeah.
will at some point understand what's going on. So
Yeah.
I think it's worth that exercise in trying to understand it yourself.
Yeah. I think I'm just thinking back to Ant Nichols from OpenAI. He said, surprises is how you learn. If you're surprised, then you have to understand what's happening. Something's doing something you don't understand. And I'm the
Mhm.
same with, if you do an XY scatter plot, just very simple. And there's an outlier. So what's that doing? Something's happening there. I don't understand. I need to explore that. I don't care
Yeah,
about the straight line. I care about that outlier, that point. And yeah, to Anne's point, that's so true discovery comes, I think. That's where
mhm.
true understanding comes, is by trying to understand the surprises.
Yeah,
Uh, in what we do.
yeah. The outliers are always the most interesting. But for the
Yeah,
generation here that's scared that AI is going to replace them,
yeah,
if all you're doing is looking at predictions and
yeah,
taking it as ground truth, then yeah, AI will replace
yeah,
those
yeah.
aspects
That's
just like they will anything else.
yeah,
Uh, our safety or um, our safety comes from being able to make those intuitive leaps that AI
yeah,
can't. Um,
yeah,
and that means that there has to be a base level of understanding. It
yeah.
frankly, in some cases, it kind of shocks me that, and it's not anybody's fault. It's just the field has gotten so large, but it sometimes shocks me how little a chemist understands about actual chemistry,
Hmm.
or has not had to go sit in the lab, or has not had to run through a synthesis. And this
Yeah,
happens more often than you would expect. And so we need to go back to those basics so that
yeah,
when you understand, and I benefited from this because I went through biochemistry,
yeah,
but I understand the biology and I understand the chemistry, and I understand the application. So I truly benefited from having exposure to all three of those areas in addition to the computational aspect. And so it
yeah,
allows me to ask different questions than
yeah,
a pure comp person might ask.
yeah. And I think that's a huge benefit as well as working in multidisciplinary teams,
Mhm.
because you can bounce ideas off each other. We've all grown
Yep.
up in different ways. We have different ideas. And it's really very dynamic. We're not 18th century natural scientists anymore. We're not doing everything. I think of the guy who was to put a teaspoon of oil on a lake, and then it formed a monolayer. Somebody will tell me who it. But I see some chemists who I've worked with in the past on the line as well. But I think,
Mhm.
yeah, I think it would be good to close here.
Sure.
Do you have any final remarks?
If you're
Close
comfortable,
sentence? Yeah,
then you're not
I'm
doing it.
comfortable always. Yeah, no, always. Yeah, I think one of the most important things as well. Every time I interview someone, it's like, do you enjoy what you do? That's
Yeah.
the most important thing. You must love it. You must get some thrill out of finding something no one ever knew before. Let's do that. Let's pursue
Mm.
that. AI will help us along the way. But
But, I when I say, are you
yeah,
comfortable? There needs to be some level of discomfort. Why don't I understand this? Or
yeah,
what's missing? And it's that discomfort, that itch that you need to scratch, I think, in order
yeah,
to move on. And I think if you are feeling that, then you're kind of in the right place. You know where
yeah,
you're headed. And as long as you keep scratching that itch to relieve that discomfort, then you're
yeah,
on the right track.
yeah. No, I agree. That's a wonderful words to end on. So thanks so much again, Essam.
Okay.
Wonderful catching up with you again. Thanks so much. I look forward to hearing more from you and the work you're doing. And thanks for all the attendees today. We'll follow up on any of the questions that weren't answered, and Sam or I will answer those. But again, thank you to Sam for his time today. It's been very informative, very interesting perspective on what we're
Thank you
doing.
all. And thank you guys for setting up the forum.
You're welcome. Thanks so much. Speak to you all soon.
Thank you.
Bye now.